Section 7.3, Trigonometric Equations. We're going to solve the equation tangent theta equaling -1 where theta is between 0 and 2 pi. Right? So we're looking for values of theta that make this equation true, but only values that are between 0 and 2 pi. So what is this telling us? This says find the angle whose tangent is -1, right? Now, tangent of theta, we know is equal to sine theta over cosine theta, right? So it's equivalent to say that sine theta over cosine theta equals -1. And that's also the same thing as saying that sine theta is equal to the opposite of cosine theta, right? If you divide two quantities by each other and get a -1, one is the opposite of the other. Okay? Since we're only looking for these angles in between 0 and 2 pi, let's use our unit circle. Alright, so where is sine and cosine? Where are sine and cosine opposites, right? Same absolute value but opposite signs. Well, that happens in quadrant 3 and quadrant 2, pardon me, and quadrant 3, right? And we know that the pi over 4 angles have sine and cosine that are both square root of 2 over 2. The pi over 4 angle that lies in quadrant 2 is actually 3 pi over 4. So this is 3 pi over 4. And the one in quadrant 3 is 5 pi over 4. Okay? So I know here that the cosine is negative square root of 2 over 2. The sine is square root of 2 over 2. Notice those two things are opposites of each other. Oh, and I'm sorry. It's not quadrant 3. Those are the same. And it's not 5 pi over 4. Pardon me. I love this erases so easily. It's going to be 7 pi over 4. So let's bring this all the way around. There we go. At 7 pi over 4, the cosine value is positive square root of 2 over 2, and the sine value is negative. So notice the cosine and the sine are opposite of each other there. Okay? So we can say that theta then is 3 pi over 4 or 7 pi over 4. That would give us those angles both have tangent -1 and they're in the interval 0 to 2 pi. Alright, let's make things a little bit more complicated. Let's say we needed to solve the equation 2 times the cosine of 2 theta equals 1. And we still want values of theta that are between 0 and 2 pi, including 0 but not including 2 pi. All right? Well, anytime you're working on these equations and there's more going on than just the trig function, you need to isolate that trig function. So we're going to start by dividing both sides by 2, which gives us the cosine of 2 theta equals 1/2. Now you might think, oh, let's divide by 2, but we can't because we're taking the cosine of an angle. Right? This isn't the same thing as 2 cosine theta. This is cosine of 2 theta, right? So what can we do? Well, let's think about what it's asking us. It's saying find the angles, theta, in 0 to 2 pi, that when we multiply them by 2 and take their cosine value, you get 1/2. It's not a super easy thing to do. What I like to do is use the substitution. The book doesn't show this, but I really like it. Let's let x equal to theta, right? So if we do that, we're saying that the cosine of x is 1/2. Now let's just solve for x, right? So which angles in the interval 0 to 2 pi have cosine 1/2? Well, it turns out that we have pi over 3 or 5 pi over 3. Get out your unit circle if you're not sure. Okay? Now what we're going to do is plug back in for x to find theta. Okay? So since x was 2 theta, we have 2 theta equaling pi over 3 instead of x, or 2 theta equals 5 pi over 3. And now we can solve both of these equations. The quickest way to isolate theta is to multiply by 1/2. You could divide by 2, but when you divide a fraction, that's multiplying by the reciprocal. So I just like to go ahead and multiply by that reciprocal. So times 1/2 times 1/2, we get theta is pi over 6 or theta is 5 pi over 6. Okay. Great. How do we check these? Well, of course, you take the angles and you plug them back into the original and see if it works. Yeah? Okay. You might ask, why are we not using the inverse functions of tangent and cosine so far? Because that's what undoes it, right? That's what finds us our angle. Well, remember that there are specific restrictions on the ranges of those functions. So we have to be careful because it's only going to find angles in the wrong intervals. Yeah, not all the way from 0 to 2 pi if we use the inverse. Okay, so that's what we don't do. All right, so what if we want solutions that are not in that interval from 0 to 2 pi? Shoot, I don't know where that ended. Let's go back. I hope that you got the formula or the solution for the last one. I think maybe it's just with this example. All right, we're going to solve sine theta over 2 equals negative 1/2. We're going to give a general formula for all the solutions and list the just six of them. Okay, we're going to use the substitution. We're going to let x equal theta over 2. So when sine of x is equal to negative 1/2, that means that x is 7 pi over 6 or 11 pi over 6 in the interval 0 to 2 theta. I'm sorry, 2 pi. So, but we want more, right? We want every solution. So it turns out that we have to think of angles that are coterminal with that, with these angles. So what is the period, right? What is the period of sine? Yeah, what is the period of sine? Well, the period of sine is 2 pi. So I'm going to change 7 pi over 6 to say 7 pi over 6 plus 2 pi k, and I'm going to turn 11 pi over 6 to 11 pi over 6 plus 2 pi k, where k is any integer, right? So if we plugged integers in for k right here, like 1 we'd get 2 pi, 2 we'd get 4 pi, 3 we'd get 6 pi, right? So that's going to be, and that's going to be adding 2 pi every time, so that's going to give us all those angles that also have sine value of negative 1/2. All right, so now what we're going to do is we're going to plug back in. We're going to now say, oh, but we don't want x, we want theta. So we know that theta over 2 is equal to 7 pi over 6 plus 2 pi k, or that theta over 2 is equal to 11 pi over 6 plus 2 pi k. And now we're going to solve for theta. This time we're going to multiply both sides by 2 to get theta alone. We end up with, let's see, 7 pi over 6 is 14 pi over 6. This 2 is going to get distributed, 4 pi k. So that's the same thing as reduce 7 pi over 3 plus 4 pi k. Or theta is going to be, same thing, we're going to multiply by 2 on both sides, 22 pi over 6 plus 4 pi k, and then 22 pi over 6 reduces to 11 pi over 3 plus 4 pi k. Right? So it turns out that this is the general formula for those solutions. You might say, why isn't it plus 2 pi k if it's periodic and sine is periodic? But remember, we're actually doing sine of half of an angle, right? And so if you were to graph the function sine of theta over 2, you would see that it ends up having a period of 4 pi. But we actually don't have to worry about that here because we're able to figure that out, find that period algebraically. Okay, now we're going to find 6 solutions. Now there are infinite numbers of solutions, right? But we're just going to find 6. So what we're going to do is we're going to take a few values of k and we're going to make 6 values because we have 2 already. So if we plug in 0, 1, and 2 for k, we're going to get 2, 4, 6 solutions. Okay? So if k is equal to 0, then theta is going to be 7 pi over 3 or 11 pi over 3. There's 2 solutions. If k is equal to 1, we're going to get theta equals 7 pi over 3 plus 4 pi, right? I'm just plugging 1 in for this k, and I'm going to do it again here. Or 11 pi over 3 plus 4 pi. And then it turns out that k equals 2 gives us theta equaling 7 pi over 3 plus, if I multiply 2 times 4 pi, I get 8 pi, or 11 pi over 3 plus 8 pi. You can combine those getting a common denominator, but I actually think that our book doesn't require us to do that, so I'm not going to. All right, we're going to solve one more equation. Example. Solve 2 cosine squared theta plus cosine theta minus 1 equals 0. You might say, what? What do we do with the square? Oh, and we're just looking for theta between 2 pi, 0 and 2 pi. Well, let's use a substitution again. Let's let x equal cosine theta. Then look what you get. 2x squared plus x minus 1 equals 0. It's just a quadratic. How do we solve that? Well, we factor. We get 2x minus 1 times x plus 1 equals 0, and that leaves us with x is a half, or x equals negative 1. So then we're going to plug back in, so that means cosine theta is a half, right? Or cosine theta equals negative 1, yeah? So again, in 0 to 2 pi only, right? Angles that have cosine 1/2 are pi over 3 and 5 pi over 3. And angles that have cosine negative 1 is just 1, and that's pi. Okay, I lied. I'm going to do one more. Let's solve 4 times 1 plus sine theta equals cosine squared theta for theta between 0 and 2 pi. Now notice what we've got here. We have sine theta and we have cosine theta. So I'm not going to be able to isolate one of those or even write this as a quadratic because they're not the same. But let's recall one of our Pythagorean identities, that cosine squared theta equals 1 minus sine squared theta, right? So I'm going to replace cosine squared with 1 minus sine squared. So we're going to say 4 times 1 plus sine theta equals 1 minus sine squared theta. Now notice I have a sine squared and a sine, so if I let x equal sine theta, I can rewrite this as 4 times 1 plus x equals 1 minus x squared, right? And again, it's a quadratic. We can multiply out, equals 1 minus x squared. I can move all of the terms to one side. We're going to subtract 1, add x squared, 0. Factor x plus 3 times x plus 1 gives me x squared plus 4x plus 3. And so I get x is negative 3 or x is negative 1. Now plugging back in, remember that x was sine theta. I'm going to say sine theta is negative 3 or sine theta is negative 1. For this one, there's no solution. Why? Remember that the range of sine only gives us values between negative 1 and 1, and negative 3 is way above that, or way below that, I guess. Which angle, again, we're only looking between 0 and 2 pi, has sine value equal to negative 1? Well, that's where the y value is negative 1 on the corresponding point on the unit circle. So that theta is 3 pi over 2. So we only get one solution, and this happens sometimes when you're solving these problems, that you get an extraneous solution.